Okay, so we're going to go through the paper 2 for the September mock, for the year 13 September mock. So each video is going to be one question at a time. And also what I'm going to try and do when I go through these questions is not just talk about the answers, but to remind us about some of the things that we've learned about what surrounds those questions and surrounds those answers. Okay, so this is going to be question 1 now, so we'll just move on to question 1. And there's our first question. We have to name halogenoalkane. So in the real exam, there is bound to be at least one occasion where you have to name an organic compound, which could be something like this. So if we think about the steps that we need to take, so the very first thing that we need to do is we need to find or decide on what the longest chain is. So start at one end, and then the longest chain is how many sort of sequential carbons, like as if you were hopping from one to the next, that you can do from one starting point to the finishing point. You're trying to find the most number of carbons to do that. So if I look at this, I can do that. So that's 5 carbons. There is actually a possibility of a different, I could have done this. That's also 5 carbons, but for the sake of the simplicity of this, I'm just going to keep it straight, and so we'll just have it right across there. And then I really strongly recommend, if we're talking about exam technique or if we're talking about exam strategies, that's probably a better way of putting it. We're trying to think of ways or ideas that are going to minimize the chance of us making a mistake. We want to sort of take as much of the load off our brains as we possibly can. And I think one thing that you can absolutely do is to number the carbons when you're trying to name a compound. And so it's something you just got to get into automatically doing. Now this is actually a symmetrical molecule. If you look, we could do a dotted line through the sort of that central bit there, and it's a symmetrical molecule. So it doesn't actually matter which side I start from, because both sides are the same. So I'm going to start from the left because, you know, that is what we automatically do on our heads. 1, 2, 3, 4, 5. Okay, so we've said it's we know it's 5 carbons, so we know that it's going to be pent. Okay. And then next thing to look at are the substituents. So what things are joined on to that main carbon chain. And if we look, we've got a methyl, and we've got a second methyl, and then the other thing that we've got is a chlorine. Now, the 2 methyls, what that tells us is that we're going to have somewhere on our name, the name of our compound, we're going to have dimethyl. All right. And if you miss out the di part when you name, then you're going to I'm afraid you've lost the mark. They're going to be very, very particular about this. And then the chlorine, that's our sort of our functional group that makes this a halogenoalkane. And they did tell us that. They've told us that it's a halogenoalkane here. So we're going to have chloro. All right, so the pink part, or the pink substituent, the chloro substituent, means that we're going to have chloro in the name. What else can we say? Well, otherwise, it's a fully saturated molecule. We know it's a halogenoalkane. So if it's halogenoalkane, then it's got that alkane part in its name. So we know that it's going to be pentane. All right. And then if we think about the numbering now, for the chloro, we can see it's on the 3rd carbon. And then if we look at the methyl groups, we can say that they are on the 2nd and the 4th. So now we've got all the different parts to our name. The next thing we have to do is we have to put those parts together in the correct way. So pentane is obviously going to be at the end, right? So that's the suffix, that's the sort of final part of the name. So we're going to decide between the chloro and the dimethyl. Now the rule here is that it's alphabetical order, right? You put the substituents in alphabetical order. But what you ignore when you're doing that alphabetical order is any any prefix that is giving you a number like di, tri, tetra, they don't count when you're thinking about the alphabetization. So when we're looking at the letters to alphabetize, we're looking at M and we're looking at C. So we can now, I think, put this together. It's going to be 3-chloro, because the chloro is going to come, the C comes before the M in methyl, so 3-chloro. And dashes separate numbers and words. So we're going to have the next numbers, and commas separate numbers. Okay, 2,4, and then dimethyl pentane. And other than esters, you don't separate words. Okay, so 3-chloro, 2,4 dimethyl pentane. So some people lost the mark, because they didn't put the di, so they didn't make it clear that there were 2 methyl groups. And some people lost the mark because they put the dimethyl before the chloro. So I'm afraid they're very particular. The only thing that they are flexible on, and obviously that's not something I would still like us to avoid the problem, but they're flexible on the dashes and commas. But other than that, you have to write it exactly as it is. All right, so now we're moving on. So this information right at the beginning, let's just sort of highlight that to make that really clear. This information right at the beginning, compound A is a halogenoalkane. Notice that comes before question part A. So really that compound A is a halogenoalkane is certainly is going to be about the bulk of this entire question. So really this is a question about halogenoalkanes. And the first thing we've had to do is we've had to name a halogenoalkane. And we know that compound A is a chloroalkane. So let's have a look at part B. All right, so it says compound A has a relative molecular mass of 134.5. The main isotope of hydrogen is H1, the main isotope of carbon is C12, and then they're telling us that chlorine consists of common isotopes, chlorine-35 and chlorine-37, of which 75% of all chlorine atoms are chlorine-35. The mass spectrum of A was recorded when A was ionized by electron impact, so that's an important point. So that means when we are, that means we're losing an electron. All right, that's how it's becoming ionized. It's just losing electrons, so the mass is not changing. Okay, not for the purpose, not when we're rounding to 134.5. The mass of an electron is 1/1800th-ish of a proton or a neutron. So it does have mass, but in terms of whenever we're doing anything at A level, its mass is essentially negligible, right? So, and then we form the A plus ions. So our A plus ion, we form our A plus ions. So draw on figure 1 the peaks for the main molecular ions in the mass spectrum of A. Now, when we do MR, we're talking about, it says molecular mass, but you can also think of it as molar mass, right? Because you've got here, you would have added up the ARs. And the AR of chlorine, if you look on your periodic table, is 35.5. Okay, so this number here includes 35.5, right? Because we know, we know what compound A is. It's the one we've just named, 3-chloro-2,4-dimethyl pentane. And we know if we were doing the MR and we were looking at our periodic table, we would be looking at relative atomic masses, and so we would have 35.5. But if we then look at individual molecules, we know that individual molecules are either not going to have a chlorine of 35.5. They're going to have a chlorine of so this, I'll try to make this clear, sorry. So this is made up where there are molecules that include 35, and there's 75% of them, because that's what they tell us in that text. And then there are other molecules where we're including 37, and that's 25% of them. Okay, so if we added all of the molecules of compound A and took an average, it would be 134.5. But if we looked at individual molecules, we'd find that 3/4 of them had a chlorine 35 and 1/4 of them had chlorine 37. And then when they're all added up, they average to having a chlorine 35.5, but none of them actually have chlorine 35.5. So if 134.5, we could say, well, it's either made, that's where we've assumed it's 35.5, but in some cases it's 35. So if it was 35, it was chlorine 35, it would equal 134. And if it was chlorine 37, it would equal 136. And we know that 75% of them have chlorine 35, so that's 3/4. And we know that 25% of them have chlorine 37, so that's 1/4. So that is a ratio of 3:1. Okay, so the mass of a mole of this substance is 134.5, but those moles are made up of, and we've used the relative atomic mass of 35.5. But those individual molecules will either have chlorine 35, which is half a unit less, or chlorine 37, which is 1.5 units more. And we know that the ratios of molecules that will have chlorine 35 or chlorine 37 are 3:1. So there were 2 marks for this. One mark is for putting a peak, or putting the 2 peaks on the correct mass, which would be 134 and 136. Okay, 134 and 136. And then the second mark was for getting, you see the lines on the graph, for getting the right proportions. So we know that 3/4, sorry, let me do that again. Let's have a straighter line. We know that 3/4 have a mass of 134 because they have the chlorine 35, and 1/4 have a mass of 136. So 1 mark for putting a peak on 134 and 136, and the second mark for having the correct heights, the 3:1. Yeah, so this is our 3. Sorry, 3:1. Okay. And this is, this is really about when you did mass spectrometry really for the first time, when you did time of flight. One of the things that you should have looked at, because time of flight was there, or the mass spectrometry proved a great way of discovering or distinguishing between isotopes, or discovering what isotopes an element was consisted of. And so chlorine is always the classic example. And it was really referring back to that, but applying it in the context here of a halogenoalkane. And that's what happens in chemistry, I'm afraid, right? There is a lot of, I think it's a good thing, but it also makes it tricky. It's a very holistic, a very joined up subject. So you can't always think of them as very discrete topics. Okay, let's move on to part C. So the reaction of A, and we have to remember that A is a halogenoalkane. All right, and then we are reacting our halogenoalkane with sodium hydroxide, and you've never had in your A level a metal in terms of a mechanism. You can see this is going to be a mechanism. If you just look further down, it says next line says name the mechanism. You've never done a mechanism with a metal, so the only thing that matters here is the hydroxide. So let's just remind ourselves of what hydroxide is. Okay, and that lone pair is very, very important. And they're also telling us what it forms. So they've given us the conditions. So if, we hopefully will remember what those conditions mean, and it's really the aqueous that matters, all right? It's the aqueous that's giving us a massive clue, not the dilute, not so much the warm. They are relevant, they are specific conditions for this reaction, but it's the aqueous. It's the aqueous that is really telling us something, okay? And then we're forming an alcohol. So if we just look down to our molecule, they've reproduced molecule A, there at the bottom left there. If we're turning that into an alcohol, we must be replacing the chlorine. So, this is a mechanism you've done so many times, or will have done so many times, and it is nucleophilic substitution. Okay, and our nucleophile, let's just remind ourselves what a nucleophile is. A nucleophile is a lone pair donor. Oh, sorry, it's an electron pair donor. This is going to come up in a later question that we go through, but that pair is important. It's not enough to say electron donor, it's an electron pair donor. And we can see on our hydroxide ion, there's our electron pair. Okay. So we've named the mechanism. So thinking also about how you're approaching these questions, a useful thing to do is to sort of like number the things that you're having to do. All right. And then I'm just going to put a 3 here. So although it says include, it is making it clear. It's not always the case that you have to include the structure of the product in reactions mechanisms in exams. So I'm going to make sure that's clear. So anyway, we're going to outline the mechanism. Now, it's nucleophilic substitution. So substitution says we're replacing something. So we're going to be replacing the chlorine. So it must be about the carbon that the chlorine is attached to. And why do halogenoalkanes react this way? So the only difference between this molecule and an alkane is the fact that a chlorine is attached to a carbon. That is the only difference, and that makes a significant impact on the chemistry of such a molecule. And that is because we have a polar bond. Okay, we have a delta plus, delta minus, and the reason for that is chlorine is more electronegative than carbon. So the electron density is drawn towards the chlorine. It's like a tug of war almost. And so the carbon now gets a partial positive charge. That's that little delta there, lowercase delta. So delta plus, a partial change, partial charge, and then we have a little delta minus, so a partial negative charge. So a partial positive charge is going to be attractive to a negative charge, right? And that is the lone pair on our hydroxide ion. So you must show, whenever you're showing drawing arrows in a mechanism, they must be from one of two things, right? This is another strategy. If you've drawn a mechanism and you want to check it, you ask yourself these two questions. Firstly, is your arrow either from a lone pair or a bond? And if it's from anything else, it's wrong. If it's from something that's positively charged, it's wrong. If it's from an atom, it's wrong. It's got to be from a lone pair, and it's got to be from a bond. So what is going to happen is our hydroxide ion, or that attacks the delta positive carbon, and so a new bond is going to be formed there between the carbon and the hydroxide ion, and so that electron pair that we're starting from will in effect, you can think of it as a dated bond, although because it's those two electrons forming, that will be the shared pair of electrons, but it's never really an example of us talking about dated bonds. And then the chlorine has got to leave, and your arrow must start from the bond. Okay, it must be very clearly from the bond. So then we have to draw our product, and so all we're doing is we're drawing exactly the same as A, but we're going to change the Cl for an OH. That is it, right? That's what we've done. We've substituted the Cl with an OH. So you are literally copying the molecule. What happens here is sometimes people just forget about the rest of the molecule. So they just go into sort of autopilot. and just draw like a load of H's or whatever. And so what they forget is this CH3, and they forget this CH3, or they may forget one of them. And then, of course, where our chlorine was is where our OH was. And please, please, please take care when you're drawing bonds and make it clear which atom the bond is to. So many times I see the line in between two atoms. This has to be, this one here, this bond has to be to the oxygen. All right, it has to be to the oxygen. And then let's just check that we've answered everything that we're supposed to answer. So we certainly have answered the mechanism. That's number one. Outline the mechanism. That's what we've done here. And then include the structure. That's what we've done there. All right. So we can move on from this question, confident that we've answered every part that we've needed to do. And honestly, people do forget to do some of these things sometimes. Okay. So we've got A reacting again. So still a halogenoalkane. Just okay. So it's still a halogenoalkane. However, our conditions are different. So this time it's hot, but the key thing here is it's ethanolic. Interestingly, they've given us a different metal hydroxide. So I wonder if that was something to try and distract us. But again, we know we've never done a mechanism involving a metal, so it's irrelevant. That, you know, potassium hydroxide, sodium hydroxide, they are ionic compounds. When they are dissolved, those ions are completely separate. And the only one we're really interested in, the only one we are interested in, is the hydroxide ion, right? And remember, OH minus, if you miss out the minus, you're not going to get the mark. If you miss out the electron pair, you're not going to get the mark. Now this time, what we're producing is not an alcohol, but an alkene, all right? So it's a different mechanism. So let's go through what we've got to do. We've got to name the mechanism. We've got to state the role of the hydroxide ions. So we're getting a different product, but it's still hydroxide that's involved. So it must be acting as it must be acting differently than the previous reaction, the one we've just drawn a mechanism for. So it can't be acting as a nucleophile. And then it asks us to outline the mechanism. Oh, sorry, get carried away by my numbers. Outline the mechanism and then include the structure of the product. So there's quite a lot of things there to remember to do. So the mechanism. Now, you know, I have to say, again, by the time you're doing these questions as a mock or as a final exam, you have done mechanisms involving halogenoalkanes so many times. And there are only two. There is nucleophilic substitution, which we have already done. And then the second one is elimination. Okay. Now, if you write nucleophilic elimination, you are wrong. If you add anything else to that elimination, you're wrong. Okay. So we've got to be very careful here. The only other thing you could have with your elimination is something that's going to refer to the role of hydroxide ions, which we're going to talk about now. Now, if we're making an alkene from a halogenoalkane, that means we are, well, as the mechanism says, we are eliminating something. The role of the hydroxide ions here, and it'll be easier to show this when we see the actual mechanism, is that it's acting as a base. So the hydroxide ions in this particular mechanism are acting as a base. By the time that you've done the acid-base equilibria topic in year 13, you'll know, and so this is going to help you a little bit when you're coming to the actual real exam. A base is a proton acceptor. That's the definition. And by proton here, we mean H+. So something that is accepting an H plus ion, basically. All right. All right. So now we are making an alkene. So we have to eliminate something. We've said that the hydroxide ions are acting as a base, so that means they're accepting a proton. That means they're accepting an H plus. That means a hydrogen has to be removed. An alkene is a carbon-carbon double bond, so we've got to have a double bond forming between two carbons. So we must have something leaving two adjacent carbons. So let's draw our hydroxide ion. Now in this instance, we can do it from either the left-hand side or the right-hand side, but we're going to this hydrogen. The pair of electrons in that bond, the carbon-hydrogen bonds, are now going to move to become the pi electrons, if you like, in what will be the carbon-carbon double bond, and the chlorine is going to leave. So one thing to remember is that in all of these, or both of these halogenoalkane reactions, the chlorine is lost. So in both mechanisms, you have this arrow. The chlorine is being lost. So an arrow from the bond of the carbon between the carbon and the chlorine onto the chlorine. Okay. But you've got to think of it like a cascading effect. So it is tricky. Now it's acting as a base because the hydroxide is acting as a base because if you look at this hydrogen here, when it's bonded to the carbon, there are two electrons, right? So let's sort of draw those. They're shared pair of electrons. That's what a covalent bond is. One of those was originally the hydrogens, or is the hydrogens. So let's, for the purposes of this, say it's the X. So that's the hydrogen's electron, and then the dot is the carbon's electron, and they're sharing. So we have a shared pair. But when you look at the arrow that's moving from the carbon-hydrogen bond onto the carbon-carbon bond, both of those electrons are moving. So hydrogen is now not left with any electrons, and now in effect it's going to be a H plus ion. So that hydroxide is taking an H plus ion, which is why it's acting as a base, or how it's acting as a base. So product. Okay, so we have to draw the product. So if we think about it, if you think carefully about it, the double bond is going to be forming here because it's a pair of electrons moving to between those two carbons, and we've lost a hydrogen off the right-hand carbon, and we've lost chlorine off the left-hand carbon. So when we draw our structure, let's change the pen. When we draw our structure again, got our H here, so starting at that end, and then we've got our, it's got to be careful, you see, CH3, and then that's where our double bond is. Okay. And so there is our product. So let's just go through, have we done everything that we needed to do? Well, we've named the mechanism, we've stated the role, we've outlined the mechanism, and we have included the structure. And if we think about where the marks come from, obviously there's one mark for elimination, there's one mark for acting as a base, then there are marks for this part of the mechanism, and then we're going to have a mark for our structure. Okay, and that is 6 marks, so that makes sense. Right. Okay. Okay, so now we're doing the infrared spectrum of figure 2. Okay, so sorry, this figure 2 is either the alcohol we have made in part C, or it's the alkene we've made in part D, right? So the two reactions that have just taken place. So please remember, these questions do build on each other. They are referring or related to things that have come before. So we've got our infrared spectrum. So what you've got to remember is in the exam, so all of the questions here we're able to rely on the AS data sheet. But when you get the end of the actual A-level data sheet in the real exam, it has the same information, just more. If we remind ourselves about the data sheet, one side of the AS version was the periodic table, or is the periodic table, and then the second side is to do with infrared absorption data. Okay, so we're going to be referring to this. It's absolutely essential. I just want to say a couple of general things about IR spectra. So this region here from 1500 on downwards is called the fingerprint region. Okay, and it's called the fingerprint region because the pattern here will be unique to every molecule. So in a laboratory where they've got a huge database of molecules, it is a great way of identifying what molecule you've got. But for the purposes of your A-level and you having to do questions, what you need to appreciate is that the fingerprint region exists, that it is unique to every molecule, and that therefore you can in theory use it as a match, as a way of identifying molecules. But in terms of you identifying molecules, so in terms of us trying to decide whether this is B or C, it is completely irrelevant. All right, it's completely irrelevant. So one of the things that we've got to take from that is these wave number absorptions here are never relevant because they are in the fingerprint region, so you will never use them. So they are there as a distractor, in effect. They are there to, not to confuse you, but potentially to distract you. If they only put the bonds that you were only ever going to use, you'd have a much smaller list and it would be much easier. Life would be much easier. But please remember, they are never relevant, okay? You're never going to use them. The other thing to point out is you will always, in any IR spectra that you look at A-level, you will always have this region. Okay, so, you know, that is what, just below 3,000, 3,000 to 2,800. Well, it's this, it's always this, okay? So this, the CH is always present, all right? It's always present. What you'll find though is when you're trying to distinguish between alcohols and acids, you can see that acids in particular overlap with the CH. So what you get, sorry, is you get that broader, because essentially the absorption for the OH acid and the absorption for the CH merge, which is why you get that very broad absorption. You'll often see you'll see like at this little spiky bit here on the right hand side of a broad absorption for a carboxylic acid. Anyway, that's what we've got. We've got CH there, so that'll always be there, and then the fingerprint region will always be there. So we are having to work out whether this is alcohol B or alcohol C. Alkene C. So key thing is what bonds are unique to those two compounds. So alcohol B is clearly an OH alcohol. So let's have a look. So if we look at OH, where OH alcohols here, it says 3,200 to 3,500. Obviously, we would use the real numbers in our answer, but just for the purpose of annotating. So if we have an alcohol, we would expect an absorption that would be where the OH is. if we look at, if it's an alkene, it's going to have a carbon-carbon double bond. So we're going to expect, it's quite a narrow, but we're going to expect an absorption between 1620 and 1680. So tricky to find that exactly, but 1516, it is roughly, oops, here. So if I just do a, that's where that absorption should be, and that is where that absorption should be. Now the thing about the carbon-carbon double bond absorption is that it is never a large absorption. We do have an absorption in that area. We do not have anything here. So it should be clear, I hope, now that we have got alkene C here. And our explanation can be one of two reasons. We can say there is an absorption, oops, in the range, and then you give the range for a carbon-carbon double bond. And so whenever you're identifying an absorption in an answer, you must either give the range of that absorption, i.e. according to the data sheet. So the data sheet tells us it's 1620 to 1680. Or you must give an absorption, a value. If you want to give an actual value, your value must be within that range. So I could have said there was an absorption at, and as long as I gave then a number between 1620 and 1680, then I would have been correct. There is an alternative answer. We could say, because you might not feel super confident about that peak at the carbon-carbon double bond peak, or maybe you're sort of slightly hesitant about it, but what you can absolutely categorically say is there is no, what I should have said, apologies, I should really make this super, super clear, which corresponds to what we're saying. Sorry, I'm making it crystal clear that I'm giving the absorption range for a carbon-carbon bond. Sorry about that. I should have, that's not great on my part. The alternative is there is no absorption for an OH, and every time you say OH in infrared, you must say whether it's an alcohol or an acid. If you just write OH, you are wrong. For an OH bond in the region, and then we should put what the actual numbers are, 3230 to 3550. So you only have to put one of these statements, and probably it would be best to go for the alkene because that's the one you're saying is there. Okay. And then this is the final part of the question. It says compound D reacts with dilute aqueous sodium hydroxide in a similar way to form alcohol B, similar way to A to form alcohol B. So the same reaction is taking place. It's a nucleophilic substitution. We are making exactly the same alcohol. We've just started with a different halogenoalkane. And then it says explain why D reacts more quickly than A, given everything else is the same. So this is what's our independent variable. Like, what is different about them? So yes, it's the halogen, but if you think about what's actually happening, what's happening is a bond is breaking. So the difference is really the carbon halogen bond. Okay, that's the difference. And fundamentally, the reason that D reacts more quickly is that the carbon-bromine bond is weaker. This has got nothing to do with electronegativity. This is about bond strength. And one of the factors in bond strength is how long the bond is. So the longer the bond, generally the weaker it is, because that means the electrostatic attraction between the shared pair of electrons and the adjacent atom's nuclei is weaker, because distance makes that electrostatic attraction weaker. And the reason that the carbon-bromine bond is longer than the carbon-chlorine bond is simply because the bromine atom is bigger. So it has a bigger atomic radius. So all you had to put here is the carbon-bromine bond is weaker than the carbon-chlorine bond. And that's it. So that's the first question. I hope it's all been really clear. I have tried to go through it carefully. I have tried to explain lots of things surrounding the questions and not just give you the answers. If you have any queries, just let me know and I'll do my best to fix them. But otherwise, I hope that was useful.